It is my pleasure to introduce Dr. Shahab Mahageg. Shahab is the President and CEO of Intelligent Solutions, Inc., or ISI, and Professor of Petroleum and Natural Gas Engineering at West Virginia University. A pioneer in the application of artificial intelligence and data mining in the exploration and production industry. He holds BS, MS, and PhD degrees in petroleum and natural gas engineering. He has authored more than 150 technical papers and carried out more than 50 projects, many of them with major international companies. He is an SPE Distinguished Lecturer and has been featured in the Distinguished Author Series of SPE's Journal of Petroleum Technology, JPT, 4 times. He has been honored by the U.S. Secretary of Energy for his technical contribution in the aftermath of the Deepwater Horizon Macondo incident in the Gulf of Mexico, and is a member of U.S. Secretary of Energy's Technical Advisory Committee on Unconventional Resources. Shahab is a designated U.S. liaison, WG4, representing the United States in the International Organization for Standardization, or ISO, for CO2 capture and storage. Shahab was an SPE Distinguished Lecturer for the 2007-08 lecture season. He was the former chair of the SPE Global Training Committee and currently is chairing SPE Book Committee. Welcome, Shahab.
Thank you very much, Stefan. Good morning, everybody. Good morning from Morgantown, West Virginia, and maybe afternoon or evening in other parts of the world, wherever you might be. As Stefan mentioned, the topic is shale asset management via advanced data-driven and predictive analytics. I will start by defining the problem first. Then I will cover some examples of pattern recognition in shale, how we can deduce patterns from data in shale. The data that in its raw form, when you look at it, does not seem to represent any specific patterns, and we'll see how with advanced data-driven analytic we can actually deduce such patterns. After that, I cover how we can use the data and these patterns in order to develop predictive models and train, calibrate, and validate these models. Once the models are developed, they can be used in analysis. I'm going to cover 4 different post-modeling analysis. First is a look-back analysis, whereby we can use the predictive capability of the model and in conjunction with Monte Carlo simulation and try to identify the best practices that we have performed in past and lessons that we learn from existing frac jobs and completion practices that we have performed in an asset. Then we're going to talk about type curve generation, whereby using this model we can generate type curves for the entire asset or for any specific region of the asset. Also, I show analysis through which we can use the data in order to evaluate the performance of the service companies that have implemented the frac jobs and completions for us. That is, of course, if you have more than one service company doing the frac jobs. And finally, I close by using the model in order to help us design new frac jobs and for new wells in the asset. So with that, the first, of course, is the problem definition. Talking about reservoir modeling and production modeling of shale, it is the technologies that are currently used are either analytical or numerical. For example, decline curve analysis is used quite often. Rate transient analysis are used reasonably often. And for those who deal with more prolific assets, reservoir simulation and modeling is one of the choices that people use to perform modeling. When you do reservoir simulation and modeling, you have 2 options. You can either use explicit hydraulic fracture modeling or you can use a stimulated reservoir volume technique. When you do explicit hydraulic fracture modeling, you use a hydraulic fracture modeling software, and you generate first things such as fracture half-length, fracture height, conductivity, and so forth, and then import those into a reservoir simulation model, and then you perform the reservoir simulation using those details. So this is a very labor-intensive process, and it takes a long time. And in the reservoir simulation model, when this is done, usually it takes, for a single well with, let's say, 20 stage of hydraulic fractures, approximately 60 clusters of hydraulic fractures. This will take up to 1 million gridlock, and therefore it's going to be quite time-consuming to develop, and then almost also very time-consuming to run. Because of that, to circumvent that process, people have used stimulated reservoir volume technology, whereby they define an area of the reservoir that is stimulated by the hydraulic fracture. And sometimes they use microseismic in order to define the size of the stimulated reservoir volume. What I need to mention is, in most recent publications and presentations that I have attended from some of the most prominent completion engineers, modelers that are very well known in doing reservoir simulation and modeling or analysis in hydraulic fractures in shale, it seems that there is a notion that people are starting to distance themselves from the idea of doing stimulated reservoir volume analysis for different reasons. I'm sure these people will be publishing their ideas about this. And as far as the microseismic is concerned, in order to use it to delineate the stimulated reservoir volume for modeling, it seems that it is quite inconclusive. From a published information, you can find as many cases whereby this has provided good results, as many you can find really poor ones, whereby the microseismic events and the way it has been processed after production logging does not match in any shape or form to what is seen in reality in terms of production. So as far as I'm concerned, microseismic, the way it is at least processed today, I do believe it's a very, very promising technology. But the way it's processed today, at least, it has some time to grow and to find its way of how to be used correctly in this technology for shale assets. Now, what I'd like to point out is that all these current techniques that I talked about, for example, I also talked about rate transient analysis. If I have to go back, the rate transient analysis that is used, essentially, it is the entire technology behind that is no different from reservoir simulation and modeling. The only thing is, it's done people have found very clever ways of performing these analyses without running the entire reservoir simulation model, and by performing some plots of different characteristics. That process is called rate transient analysis. I know it, and of course, decline curve analysis. Everybody knows the limitation of